High-speed hardware and massive data sets provided the raw power for the modern AI explosion. But bridging the gap between that power and scientific discovery required a change in the interface, an evolution in how researchers interact with code in real time. Traditional software engineering is built on a cycle of writing, compiling, and running entire scripts. This creates a barrier for scientists who start with a hypothesis rather than a final requirement. They need to test an idea, inspect a data anomaly, and receive immediate feedback to determine their exact next step. In 2001, physicist Fernando Perez created IPython to address this specific scientific workflow. He wanted a system that accommodated the iterative, often messy process of empirical research. IPython allowed users to explore objects deeply and integrated rich media outputs, like charts and mathematical equations, directly into the coding environment. By combining the code with its immediate visual results, the system prioritized the human cognitive process of discovery over the machine's requirement for pre-compiled instructions. As the community grew, developers sought to apply this interactive model to languages beyond Python. This led to the 2014 Big Split, where the core team systematically severed the visual interface from the underlying computational engine that executes the code. This diagram shows the resulting decoupled architecture. The front-end web server acts as a hub, sending data payloads over a specialized protocol to distinct engines running in the background. This independence allows a single platform, Project Jupyter, to support over 100 distinct programming languages, including R and Julia. This diagram shows the notebooks format, a JSON document. It encapsulates source code, markdown text, and execution outputs into distinct notes. This enables literate computing, where code is embedded within a narrative. Zooming into the output node reveals the MIME bundle architecture. The engine returns multiple representations of the same data simultaneously: plain text, a static image, and an interactive format. The front-end interface checks the local environment and automatically selects the richest format it can render. If a specialized library is missing, the notebook displays the static image instead of failing. By packaging code, context, and multimodal results into a single structured file, the architecture creates a shareable and reproducible computational story. For years, notebooks were primarily research tools, but as they moved into mission-critical production pipelines, their interactive design revealed significant vulnerabilities in software stability and reliability. The central issue is the hidden state. Let's look at this comparison. On the left, a notebook appears as a linear document. On the right, however, the engine's memory remains persistent and mutable. Because users can execute cells in any order, the visual layout on the screen often differs from the actual state of the variables in memory. If an analyst sets a variable in step 2 and then deletes that cell, the command vanishes from the visual document. But as the highlight shows, that variable remains active in the system memory. When the file is shared and run from top to bottom, it produces different results or fails entirely, breaking the scientific method. The JSON file format also creates friction with version control systems like Git. Because notebooks store execution counts and image metadata in the same file as the code, a simple run without any logic changes generates massive, unreadable diffs. This makes code reviews nearly impossible and leads to constant merge conflicts. The flexibility required for exploration often conflicts with the strict requirements of automated, reproducible software systems. To bridge the gap between science and engineering, the industry developed Notebook Ops, a set of tools designed to enforce production-grade rigor. New libraries allow developers to compile designated notebook cells into standard library modules. This keeps the interactive interface for exploration while generating clean code that integrates into automated deployment pipelines. For automated execution, the industry uses parameterization. As shown here, a single notebook acts as a template. The system injects different variables, like date ranges or geographic regions, creating a grid of parallel runs that each produce a distinct, immutable audit trail. Cloud platforms use this architecture to manage hundreds of thousands of analytical jobs. Organizations like Netflix rely on these systems to run algorithmic experiments and manage data pipelines at a global scale. To enable secure collaboration, the platform integrated conflict-free replicated data types, or CRDTs. By assigning a unique ID to every cell, the system allows multiple users to edit the same document concurrently, ensuring all versions eventually align without data loss. These operational safeguards have converted the exploratory research sandbox into a governed, collaborative enterprise tool. By 2026, the enterprise landscape is defined by managed cloud platforms that enforce strict versioning for both code and data. This ensures that every insight meets the audit requirements of modern global regulations. While some code now runs directly in the browser using WebAssembly, the memory demands of large-scale data engineering still require traditional server-backed architectures. This provides the necessary power for complex model training and massive data transformations. Inside these environments, frontier large language models interface with the workspace through standardized client protocols. As shown in this schematic, a central AI node possesses direct connections to the local file system, active data tables, and the execution terminal. These protocols enable agentic tool calling. Instead of just suggesting code, an AI agent can execute a cell, read the resulting error traceback, and autonomously modify its logic to fix bugs in real time. Because the notebook maintains a persistent memory state, specialized AI agents can use the environment to hand off tasks to one another. One agent might clean the dataset, while another builds a visualization, communicating through the notebook's underlying state. As AI agents take over more of the iterative coding and debugging, the role of the data scientist is shifting. The notebook, once a tool for manual experimentation, is becoming a supervisory dashboard,